So in the last couple of videos, we went ahead and approached the Pythagorean theorem from an algebraic point of view. We were using the Pythagorean theorem to solve for the sides of a right triangle. We are now going to go ahead and look into proving the Pythagorean theorem, and we're going to do this multiple ways in these videos. So we're going to start first with a proof by an Indian mathematician called Bhaskara, and to the right is the image that's going to help us out. So first we're going to notice if we take, for example, just this right triangle, and here is the right angle, and if we label this A, and this B, and this C. So this is a hypotenuse. From here to here is C. From here to here is A. And from here to here is B. Now, if we were to take the same triangle and make 3 more copies of it and rearrange them around, we get this configuration. And so notice that the hypotenuse is on the outside. So for example, from here to here is also C. And from here to here is also C. And from here to here is also C. So this is A, this whole length. So from here to here is A. Here to here is A. And here to here is A. And then the short length is going to be B. Let's try a different color for that. There's B. There's B for this one. This can get a little confusing if you're not careful. And there's B for that one. Now, one more thing that's interesting to find and that we need to find is this inside square. And how long is the side of one of the sides of this orange square in here? Well, it's not B because that's out here, and it's not A because A goes from, for example, from here all the way down to here. However, if we look, for example, this whole length is A, and this amount is B, we could express this entire side as A minus B. You might want to pause the video to kind of make sure that makes sense. And you might want to redraw this yourself to see how that works out. But I'm proposing to you that A minus B is this length right here. You could also look at it from this perspective where this entire side from here to here is A, but I'm trying to go ahead and remove this amount from it. So that makes this side right here from here to here A minus B as well. And because it's a square, right? A square is a regular quadrilateral, then all the sides are congruent. So every side on this square is A minus B. Let's set up a relationship among all these shapes. So we're given the right triangle, ABC. We took that red triangle, we made 3 more copies of it. We took the 4 triangles, rearranged them to make this diagram, and in such a way that the hypotenuses are all on the outside of this larger square. So we have this outside square is equal to these 4 triangles plus the area of this square in here. So what we're proposing is that this larger triangle is, this larger square is made up of 5 shapes. It's made up of the inner square and the 4 rectangles. Triangles, sorry. And so we've created this equation based on the geometry that we see. So the 5 inner shapes make up the 1 outer shape. So what is the area of the outer square? Well, that's going to be C squared. There are 4 triangles. So I'm going to do 4 times the area of one of the triangles. So if we look at the original triangle here, and this is the right angle right here, its area of a triangle is 1/2 times the base times the height. So the base is B, height is A. And what about the inside smaller square? Well, that's A minus B. It's going to be A minus B squared. And we're going to simplify this. So let's simplify this sum. This ends up being C squared, no big change there. Half of 4. This gives me a 2. So that's 2. I'm going to put this in alphabetical order. So 2AB. And before you do some funny stuff with this binomial, recognize that this square belongs to the entire A minus B, not just a A or just a B. This is saying that this whole package is multiplied twice. So I'm going to write this out the long way to make sure we do the algebra right. And if we go ahead and FOIL that, you're going to get a squared minus 2ab plus b squared. Now, notice that here's a positive 2ab, here's a minus 2ab. They cancel out. And I'm left with c squared, a squared, plus b squared. And we have proven the Pythagorean theorem. So when I was going to UCLA as a mathematics student, I'd go into this building all the time for my classes, and in particular, there was this one classroom, and I remember looking at the floor and realizing, oh snap, that's the Pythagorean theorem. Problem 2. This is not Bhaskara. This is a more traditional Pythagorean theorem proof. We start with the same given, a triangle ABC. So imagine, if you will, that we start with this triangle right here, and it's a right triangle. It has legs AB with a hypotenuse of C. We make 3 more copies of it, and we have a total of 4 right triangles, and we arrange them in such a way that we get this shape as you see before you. Now, the convenient thing about this is that we have the C, the hypotenuse, is on the inside instead of the outside. Okay, and maybe if you struggle a bit with problem 1, problem 2 should be a little bit more approachable. And after you understand problem 2, it would be encouraged for you to go back to problem 1 to review problem 1 to see how some of the algebra was set up and how some of the geometry revealed the equation that we got before. So we're going to prove, of course, the Pythagorean theorem: c squared is a squared plus b squared. And if you'd like to pause, take some time to see how the shapes stack up against each other. So, for example, the big square here. What is that made up of? What kind of shapes make up this square on the outside? So here's what we're looking at. There's 5 shapes total, the 4 right triangles, and then the inner red square. And so if we had these pieces, we could rearrange them in such a way that they would form this large blue square that you see on the outside. So let's go ahead and take care of these. Area of the 4 triangles, that's going to be 4 times 1/2 base times height. Base is A, height is B. The inside smaller square is C squared. That's the area. Now the outside square, see, from here to here is B. And then from here to here is A. This should remind you of the segment addition postulate, right? The segment addition postulate says you can add those line segments together. So that's what I'm proposing to you, that this side from here to here is A plus B. And because I want the area, it's squared. A times B times A times B. If we go ahead and do our math, 4 and 1/2 is 2, AB. The C squared is C squared. And then A plus B. If I FOIL that, I'm going to get A squared plus 2AB plus B squared. Now, this looks a little different than last time. We have a 2AB here, we have a 2AB here. If I subtract this to the other side, they cancel out. And I'm left with C squared equals A squared plus B squared. Ah, snap. Very good, very good. For your summary, explain the relationship between this idea of a square from geometry, as in the actual shape, and the algebraic word that we use, squared, when we use to describe exponents. And don't forget in your discussion to include the word area.